Now let's talk about electron diffraction. Okay, electron diffraction is shown in Davison-Germer experiment. Okay, so Davison-Germer experiment is trying to prove that electron, although it is a particle, it also shows wave property. Okay, because electron also exhibits diffraction pattern. Diffraction is actually a wave property, yeah, which is the picture I show you in earlier on. This is the electron diffraction. Okay, so this diffraction pattern is a wave property, proving that electron can behave as wave. Electron behave as wave in Davison-Germer experiment, yeah, under the electron diffraction. Understand? So electron behave as wave, not just particle. Electron behave as wave in the electron diffraction by Davison-Germer experiment. Okay, so let's go back here. So in Davison-Germer experiment, it shows that electron can exhibit diffraction pattern, showing that electrons also has wave property. Yeah, also have wave property. So if you can see, this is the electron diffraction tube. Okay, electron diffraction tube. So here you have a cathode and anode. This is the accelerating chamber. Okay, I will explain later on. Accelerating chamber is to accelerate the electron. Electron will shoot up from cathode, accelerate towards the anode, and then after that, electron will pass through the graphite film, and it will undergo diffraction. Yeah, after passing through the graphite film, it will diffract. It's like graphite film is like a diffraction grating. You understand? The graphite film is just like a diffraction grating, so it will diffract, and then it will show rings. Yeah, like which is what is shown over here, like this one. Yeah, this one will be catch on the screen. Yeah, what you can see here, the white color here, this is called the fluorescent screen. Yeah, when the electron beam strike this fluorescent screen, yeah, fluorescent screen, it will emit green light. It will emit green light. Okay, but here you can see this is the voltage here he applied. Yeah, he applied 5 volt. Yeah, here he applied 5 volt, and this is for the accelerating chamber. Yeah, accelerating chamber. Why we have potential difference 5 volt? Is to accelerate the electron. Why we need to accelerate the electron? That's a very good question. Yeah. So now we're going to learn. Okay. Okay. So here. So here it shows diffraction pattern on the fluorescent screen. Yeah. When the electron strike the fluorescent screen, it will emit green light. Here you see. So at first here, why we need an accelerating chamber? Why we need to emit accelerating chamber? What is actually accelerating chamber? Yeah, over here. This is this part. Okay. In fact, this part, yeah, cathode and anode. This part is the accelerating chamber. Yeah. This is the cathode, and this is the anode. Okay. Electron come out from cathode, and anode is the collector. Okay. So okay, so how is the electron being accelerated? This is like the very basic knowledge in chapter 1, electrostatic. This is actually basically like conservation of energy. Conservation of energy is from electric potential energy convert to kinetic energy. Because when electron very near the negative charge, very near the negative plate, it experiences a very high repulsive force, and it has very high potential energy. So this electron will be attracted. It will experience a electrostatic force. It will be attracted to the positive plate, and also it will be repelled by the negative plate. Because it is being attracted by positive plate, repelled by negative plate, so this repulsive force of attractive force will accelerate the electron towards the positive plate. That's why the potential energy, initially it has very high potential energy, it will all convert to kinetic energy. Yeah, this potential energy will convert to kinetic energy. So as the electron move towards the right, the potential energy will drop, and it is converting to the kinetic energy. The kinetic energy will increase. So this is actually conservation of energy, potential energy changing to kinetic energy. Yeah, actually this accelerating chamber, you can see later I will talk about this. This one, actually this formula, previous video I explained about this. I did show you a little bit in the de Broglie wavelength. I did show you about this. Why the kinetic energy here I changed to EV. Actually is because of the accelerating chamber. Okay, the delta U changed to delta K. Delta U is Q delta V, and the charge we use is electron charge. That's why Q equal to E. The delta V is the potential difference, V. So K is equal to EV. That's why we can substitute K with EV over here. See here? Here you can see EV here. Actually is for the K. Okay, let's go back to this one, electron diffraction. So this one, you see, this Q actually is this U is actually Q times delta U, delta V, sorry. Okay, Q times delta V. So Q is the electron charge. Yeah, we are using electron, and this V is actually delta V. But we simplified. We don't write delta V. We just write V. Yeah, but we can understand this V is actually delta V. Delta V means the potential difference between the two plates. Potential difference between the two plates. That means if this negative plate is 0 volt and this positive plate is 10,000 volt, so the delta V is 10,000 minus the 0. The delta V is 10,000 volt. That's the let's say, just want to make it black color. Yeah. So that's the delta V, the potential difference between the two plates. All right. So now if I apply a very high voltage here, if I apply 10,000 volt potential difference, K is equal to half mv square. We can see if high potential difference, in the end you have high kinetic energy. In the end you will end up with high kinetic energy, and also the electron will be accelerated to a very high velocity. So this electron will have high kinetic energy and high velocity because of high potential difference, because of the delta V is very high, 10,000 volt. Yeah, so this electron has high energy. Yeah, we can say this electron has high speed and high energy. High speed and high energy. That's why we learn something like we call in if you further your study, you will learn about this high energy physics. High energy physics is all related to this accelerating chamber. High energy physics, where we learn high energy particle. Yeah, here I purposely put a large hadron collider. It's all because of particle accelerator. Yeah, just now you say this is a very actually this is the simplest accelerating chamber. You just use two parallel plate with a negative plate, positive plate. Accelerate the electron by using the electrostatic force, the Coulomb force, yeah, electrostatic force, by using electric field. This one even more complex. Yeah, I'm just showing you the simplest accelerating chamber. Here you have a very large accelerating chamber where just now you say you use the high voltage, high potential difference to accelerate the electron to a very high velocity, high kinetic energy. This one also accelerate the Large Hadron Collider will accelerate the protons, the ions, to near the speed of light. You see, this is why is it called Large Hadron Collider. Why is it large? Yeah, it's actually at the Switzerland, Geneva. Why this Large Hadron Collider is very large? Because it is 27 kilometer long. You imagine 27 kilometer long. How long is it? Yeah, this is the Large Hadron Collider. Yeah, it's almost a town. Yeah, a state. the size of a state. In future, Large Hadron Collider, they want to build an even bigger one with 100 kilometer long. Now it's just 27 kilometer long. In the future, they want to make a 100 kilometer long. That will accelerate the protons to even higher speed. Can you imagine this accelerator can accelerate the protons or ions to near the speed of light? How fast is the speed of light? Speed of light is 3 exponent 8. You want to accelerate this particle to near the speed of light. Later, these protons or ions will bombard with another particle, and then they will break up into these elementary protons. You can investigate what is the structure inside a nucleus, what is the structure inside a proton, a neutron. That's why they built this Large Hadron Collider, is to look into this, what we call particle physics, is to learn more about this particle physics. Okay, particle physics. What is now you think that particle physics is the smallest particle is actually a proton, a neutron, but actually Large Hadron Collider, they found out that proton is not the smallest. There are even smaller things than proton, like quark, muon, So all these are particle physics, This is why they need the particle accelerator to accelerate the electron to very, very high speed. Now I'm just showing you the simplest structure, which is just a positive plate and negative plate, can accelerate the electron to a very high speed. The concept is very simple. High potential, the potential energy convert to kinetic energy. Why this electron has high potential energy? Why this electron has high potential energy? Because of the large potential difference between the two plates. When you apply a very high potential difference, like 10,000 volt between the two plates, this electron will gain a lot of potential energy. And once released from the cathode, this electron will be accelerated towards the anode and end up with a very high kinetic energy and very high speed, very high velocity. Okay? So now, why do we need to accelerate the electron to a very high velocity? Because according to the de Broglie wavelength, de Broglie formula, okay, the wavelength is inversely proportional to the velocity. Here I can say the wavelength is inversely proportional to the velocity. That means if the higher the velocity, the lower the wavelength, the smaller the wavelength becomes. And we know that at very high velocity, the wavelength of the electron, this is actually the wavelength of the electron, will become very, very small. And according to the diffraction grating, this is d sin theta equal to n lambda, a formula from the diffraction grating that we learned before. Remember this diffraction grating? Diffraction grating, we learned about this d sin theta equal to n lambda. We know that if the smaller the wavelength, the smaller the theta. That means if form the fringes like you see if the original theta is this one, this is the original theta, and now you have a screen here, so you will form fringes over here. You form fringes over here. But when you use a smaller wavelength, you will get a smaller theta. Smaller theta means now the light will shoot this way. The light will have a smaller theta. We will shoot over here. I will shoot over here. This one just now, this one is for big theta. Now with a smaller theta, you can see what? You can see the fringes are closer to each other. The fringes become the fringe become closer to each other. If what you can say is if very big wavelength, you have a big theta, that means you can see your fringes further apart. Okay, but if you have a small wavelength, small theta, you can see the wavelength closer to each other, very smaller size. Understand? This is for smaller wavelength. Okay, now go back to this one. So once you have a smaller wavelength, you will have a smaller theta. So the diffraction pattern become smaller. The diffraction pattern become narrower, and less diffraction. Yeah, that means less diffraction and sharper image. You will get a sharper image and higher resolution. So what's the reason why you want to accelerate the electron to a high velocity? Because you want to get a smaller wavelength. You want to get a smaller wavelength so that you have less diffraction, you have a sharper image and higher resolution. This is especially important for the electron microscope. If you want to observe a sharper image, a higher resolution, you want to observe a smaller microorganism, you need to have this accelerating chamber that accelerate the electron to a very high speed. At very high speed, you have a small wavelength, less diffraction, and a sharper image. Okay, here there is a formula to relate directly wavelength to the voltage, which I derived to you before. Okay, here you see EV equal to half mv square, and then lambda equal to h over mv. These two formula, if you combine, EV equal to half mv square and lambda equal to h over mv, if you combine these two, you will get this formula. Just now I told you that high voltage, you get high velocity, and then high velocity, you get a low wavelength. Yeah, I can just write over here, so I can just rub off. Okay, so again, high voltage, you get high velocity. At high velocity, you get a small wavelength. A small wavelength is important to get a sharp image. Okay, so you see, voltage, increase the velocity, decrease the wavelength. So to relate voltage directly to wavelength, we use this one. You see, increase the voltage, decrease the wavelength. You see or not? Increase the voltage, decrease the wavelength, just like these two formula. Now is a 2-in-1. This formula and this formula combined, you get this formula. So if high voltage, you get a high velocity get a small wavelength. Similarly, I can say high voltage, you end up with smaller wavelength. The smaller the wavelength, the sharper the image. Which I show. Maybe I straight away jump into here. What I say just now about the sharp image. Still remember last time I told you about this diffraction. Maybe you can go back to this chapter 8. Chapter 8, I did talk about this Eigen Principle to you. Okay, Eigen Principle, path difference. Where is it? Let me see. Eigen Principle, yeah. Where is it? Maybe where is it? I should. Okay, maybe never mind. Let's go back to this one. Yeah. What I want to say is, last time I did tell you in the physical optic, I did tell you the wavelength influence the diffraction, isn't it? If let's say you see this one, this is a single slit. If let's say you have a very small wavelength, the size of the slit is very big, yeah, compared to the wavelength, then the diffraction is very little, very less diffraction. If this is a very small wavelength, you get less diffraction. Less diffraction is good. Less diffraction is good. You get a sharper image. But if your wavelength is too big, it's just like this d sin theta equal to n lambda. If you have a small wavelength, that means it will form the image over here. Yeah, it will form, let's say the image, it will just form over here. The small, maybe the theta is very small. Okay, very small theta. So you get a sharp image. But if you get a big theta, that means it will form the theta is yeah, compared to this, you get a big theta. You get a big theta. Yeah, and the below also you get a big theta. So you get a blur image. Yeah, because a lot of diffraction. Yeah. So I just want to conclude that if you have a small wavelength, you less diffraction because your theta is small. Less diffraction. So here is not much diffraction at the side. Not much diffraction. Here you can see a sharper image. That means you can see the let's say you want to see the image of a cell. You don't, this is the cell. You see a sharp image. Less diffraction means you see the edge is sharp. You see the edge is a sharp edge. You get a sharp edge. But more diffraction means is blur. That means the side is not sharp. The side is a blur. Yeah, still the same thing, but you see it blur. You see the side got blur light. You understand or not? Blurry image because of diffraction. Yeah, because actually the things is he want to this is the actual shape. This is actually the actual shape. But there is extra light over here. See, there's extra light over here. That's what makes the blurry image. That's what makes a blurry image. But here there's the image is sharp over here. You see here, this one, the image is sharp. Image is sharp over here. Yeah, image is sharp over here, and at the side here there's no extra light. There's no extra light because the light is not diffracted. The light is less diffracted, so you see a sharp edge. Yeah, instead of this one, the light the image should be supposed this size, but due to this slit, but you see extra light at the side. Extra light at the side making the image blur. Because it's more diffraction. If you have a very big wavelength, so the side here, the wave at the side here tends to diffract away from the side of the slit, diffract away. That's why you see a blur image. Understand? So the smaller the wavelength, smaller the angle theta. Smaller angle theta, less diffraction, sharper image. So less diffraction is good. Less diffraction is good to observe sharp image. More diffraction is bad. It's not good. More diffraction makes the image blur. Yeah, the longer the wavelength, the bigger the theta, more diffraction and blur image. Okay, we will talk about this compare between electron and microscope later. Optical microscope. Yeah. Okay, so I think that's all for this. So you asked me why we need an accelerating chamber. It is to apply a high voltage. Okay, remember, apply a high voltage. So that has a I can just simplify over here. So you have a high voltage to get a in order to get a high velocity. In order to get a high velocity, this is about voltage, and this is the velocity of electron. And then why I want the high velocity? So because according to the formula h over mv, okay, when you have a high velocity, you have a very small wavelength, and small wavelength is good. Okay, small wavelength means what? Small wavelength means less diffraction. Less diffraction, and you get a sharper image. You get a sharper image. So you can achieve that means for this one you can achieve very small wavelength for electron by using accelerating chamber. Okay, so now let's move on to the next video.